everyone, welcome to Math Spellbook. I'm your host Peter, and basically we are going to continue on with our lessons from Sascha. So let me just get into the Discord chat with him soon. But if you're watching this on YouTube, don't forget to hit, if you like math or physics, or both, or you just need a productive stream to keep yourself occupied with the stuff that you're working on, just remember to drop a like, subscribe, and hit the notification bell, in addition to put a comment down below if you want to basically just tell us what you think of the video, as well as maybe give your own little commentary about maybe you're on your own little journey, and let us know what exactly is it that you're doing. But if you're in Twitch, as I'm streaming this right now, you can just basically talk in the chat, and basically if you have any questions for Sascha or me, you can just basically put it into the chat if you like. But welcome. So let's get to this. Hey Sascha.
Hey.
Alright, the floor's all yours.
Alright, so last time we did introduce the notion of a convergent sequence, and this was the definition. So we're gonna assume MD is a metric space, but in the back of our mind we can think of we can take M to be Q and D to be the difference in absolute value of X and Y.
Mm-hmm.
And the definition was something like that. So for all epsilon, there exists some rank, such that for all greater rank than our big N, we have that the distance between, or maybe I should have put the hypothesis that Xn is a sequence inside of M.
And N is just basically an abstract set, right? It's not the natural numbers, right?
Yeah, could be anything with the distance function that satisfied the hypothesis that we gave last time. So we had oh, you mean the big N here?
Yeah.
No, the big N here is just a number, just a natural number.
Okay.
Yeah, I thought you said the M.
Oh, no. The N. So is the N the actual natural numbers?
Yeah, that's a natural number. That's not there's this is just like a natural number.
Okay.
Not the natural number, not the set of all natural number, like a number.
Okay.
And basically, at least the way we should think about it is that if we have our point X, we can look at the little ball of radius epsilon.
Mm-hmm.
And what this definition is telling you is that so you have a sequence, we have a point like that.
Mm-hmm.
And at the start, your point can be very far from X, but at some point,
mm-hmm.
when we reach the rank X of big N,
yeah.
All further rank will be stuck inside of this ball.
Okay.
And that's pretty much the definition. And last time, we basically showed a few properties. Like we showed that if our sequence converge, then it must converge to a single point. It cannot
Mm-hmm.
converge to two different points.
Okay.
And this time, last time I said I'm going to introduce Cauchy sequence, so that's what we're going to do this time.
Okay.
And maybe I can give you the intuition first.
Mm-hmm.
So the idea, or maybe I should not put the word fell, but the idea of a Cauchy sequence is that there should be a very nice sequence, and they should be convergent if there is no hole.
Okay.
So maybe I can write it. So Cauchy sequence are a clever way to write down the notion of convergence without mentioning the limit. The limit point. And here I'm gonna put some quotation mark on the word convergence, because what we're gonna see today is that it's not always true that Cauchy sequences are convergent, and usually if that's not the case, then it means your space has some pathological problem with it. And we're gonna see that Q has this pathology that we're gonna try to solve by introducing the real number, which are gonna be like a better version of the rational number with respect to that.
Okay.
So let me introduce the definition. And as I said, the important part of Cauchy sequence is we don't have to mention what's the limit point. Okay.
Okay.
And I mean, beside from them to be like a clever way of writing the convergence criterion in like kind of a more fancy way, they will be very useful when we talk about series.
Okay.
Because usually when you do series, you don't really know which points your series is converging, right? Usually it's very hard to figure out what's the actual limit. For example, this guy is a famously if we have the following. So Cauchy is a famous French mathematician. Is that a word which is hard to pronounce in English?
Cauchy?
Yeah. Or is it fine?
Seems fine to me.
Okay. Okay, because I saw people like kind of butcher his name a few times. So
I think it's because it looks like the English word. It almost looks like crunchy. I think that's why people in English kind of find it hard to pronounce it correctly.
Oh, sometimes also I heard as if it was like some kind of couch.
Oh, Cauchy, yeah. No, yeah, because like the C and the A and the U, they kind of make that noise. Yeah, they kind of make that pronunciation sound like Cauchy. Yeah, I can see that too.
Yeah, I mean that's a very French name. His full name is Augustin Louis Cauchy, which is even more French sounding. So.
Like I think it's because like I was into math. I always hear it said as Cauchy, and I was like, okay, that's probably the way to pronounce it.
I kind of like the when people say Cauchy. It feels cozy. All right. So basically, we're gonna have something similar. So we're gonna have an epsilon, and we should think of some kind of error, some tolerance. And I mean, as for the convergence sequence, we're gonna have at some high rank, something gonna happen. And here the condition will be a little bit different. What it will be is that for every P and Q, which are greater than our big N, okay, we have that the distance between XP and XQ is less or equal to epsilon. Okay, so here I haven't written it, but PQ and N are all natural numbers.
Okay.
So this is the definition of being a Cauchy sequence. Okay. So you can sort of think of them. I mean, basically, at the end of the day, those should be convergent sequence. But if you just try to interpret the definition as the way it is, you will probably imagine something like I have like some kind of xn, right? And all the rank which are further than xn, like say xn plus 1, will be contained inside of this ball. Okay. Of radius epsilon. So it's going to be something very similar to convergence sequence. In fact, we kind of need to do a reality check. So if Cauchy sequence are supposed to be convergence sequence, then we should probably expect that convergence sequence should be Cauchy. And that's that's an important lemma. Important fact. Important lemma. Every convergent sequence is also Cauchy. Okay.
So it is x n plus 1 and x n plus 2 are the n plus
oh yeah, they're supposed to be in the lower
subscripts. Yeah, they're subscripts, right?
Yeah. So they're just like elements inside of a sequence. Okay. Important lemma: every convergent sequence is also Cauchy, and this is like one of the important facts. So we're gonna prove that. So we're gonna pretty much use the same trick we did last time. So let me just recall. So we want to show that every convergent sequence is Cauchy. So I mean, what we want to show, what we want to start is with the convergent sequence. So let's xn. Be a convergent sequence. Converging sequence, sorry. Inside of M. And what we want to show now is that xn is Cauchy. We want to show that xn is Cauchy. That's our goal. Okay. And so basically we're gonna just basically rewrite the definition. So what it means for this to be a convergent sequence, well, so let's maybe start with let's maybe start with an epsilon. So let epsilon be greater than 0, and that's kind of like usually how you start proof analysis. That's kind of a very famous wording used here.
So is that like default mostly when you start proofs and like real analysis? Is like you always write like let epsilon be greater than 0?
Yeah, almost. So let epsilon be greater than 0. So the goal, so I'm gonna write. So our goal is to show that xn is Cauchy, right? So our goal now is to show there exists some natural number n such that for all p and q which are greater than big N, we have that the distance between xp and minus distance between xp and xq is less or equal to epsilon. Okay, that's our goal. Okay, so we need to find this big N. Okay, obviously if it was like some kind of like just some sequence which has no nice property, then this would probably not be true. So we probably need to use the hypothesis that our sequence is converging.
So we have to show that there exists a natural number n that is greater than 0, that all p and q that are greater than or equal to n, there's a distance from a point in p and a point in q that is less than or equal to epsilon, right?
Yeah, the distance between the point xp and the point xq are less or equal to epsilon.
Okay.
And let me show you how it's done. So we're gonna use the fact. So using the fact that xn is convergent to x, we have there exists some big N greater than or equal to 0, such that for all rank n which are bigger than big N, we have that the distance between xn and x, and I mean if we were like so I'm gonna basically use the same trick I used last time. So we kind of have a very similar argument when we were talking about if the limit is unique here.
Yeah.
And the trick was not to use epsilon directly, the trick was to use epsilon over 2. And I'm gonna reuse this thing.
Is that usually like the trick, like within like a majority of proofs, or is that just like something you just learned from like certain proofs?
It's something like that you have to learn a little bit.
Okay.
Because I mean here I'm kind of cheating because I already know like how the proof goes, and I know at some point I will use the triangle inequality 2 times, so I'm gonna have like some epsilon 2 bounds 2 times, so I'm gonna get the epsilon that I want here. That's why I'm able to do a well guess that epsilon over 2 is probably a good choice.
Okay.
But usually you can put epsilon, and in the end you will end up with 2 times epsilon, so you can say, oh well, if I change my epsilon for epsilon over 2, then I'm fine. Okay. But this trick you will see a lot of times. Okay. And now that I have this, now what I can do, so now I want to show what it is on red, so what I will do is I will use the big N here. I will take this to be the big N I want in my goal. So let's P and Q be greater or equal to N, okay? Now all I have to show is this inequality hold. That's the only thing I need to complete the proof. And the way I'm gonna do it is I'm gonna use the triangle inequality because that's kind of the only thing I have. So here is how it goes. So we have the distance between xp and xq is less or equal to the distance between xp and x plus the distance between xq and x. So this is the triangle inequality. This I can write by triangle inequality. Okay. But as p and q are greater than n, I can use the little inequality star.
Okay.
On those 2 guys, right?
All right.
Because my rank is bigger than greater than. So what I get is I get a bound. I get the following bound. I get that each term is bounded by epsilon over 2.
Okay.
And now you see where the epsilon over 2 come from. This is exactly for this reason. When I add those 2 together, I just get epsilon, and then so basically I just shown that dxp minus the distance between dxp and dxq is less or equal to epsilon. So therefore, xn is Cauchy. So right now we don't have like much to do. Like so in analysis, usually you don't want. Like, I mean, if maybe I want to explain a little bit of the philosophy behind like those kind of proof.
Yeah.
Usually you want to control this quantity, the thing you care. For example, you see dxp, dxq. But usually you cannot know like for like what is the distance like precisely.
Yeah.
Okay. But that's completely fine. All you need is to find some bounds on it.
Right.
And I mean, kind of like the most basic thing you can do to find bounds usually is to use the triangle inequality, just like I used there.
So basically use the triangle inequality when you want something, I guess, like, let's say right now we have like the distance between xp and xq, right? So
yeah,
the bound is that there's like like I guess like an x in somewhat. So it's like that's why you have like xp to x and then xq to x, right?
Yeah. And the point is that this guy I control I have a bound also for this guy.
So let's see here. I'm just like overlooking. So like I know you used x, and basically you just had like the distance from like xn to x. So I'm guessing like xn is supposed to be, I guess, like the overall criteria, because like p and q are supposed to be greater than or equal to n, but we're sort of treating it as like xp is like still equal to like say like it's like equal, but it could be greater than like say xn, right?
Yeah. So here in this inequality holds for every n which is bigger or equal to big N.
So this is just from my own mental map, right? So is p and q compared to like n, right? So is n treated as sort of like, I guess, like a subset of numbers for p and q to take on, or is it like p and q are supposed to be like, I guess, like the sets that contain n in this case?
So p and q are just, so big N is just a number, and p and q are just bigger than big N.
It's just you use small n for like the subscript.
Yeah. So.
Right?
Yeah, so the little n here is just like a dummy variable. It just means like, I mean, this equality here holds for every little n which is bigger than big N. So what I did here is I specialized this inequality to the case where, n is equal to p and n is equal to q, which all because I mean p and q are by hypothesis bigger than big N.
Okay.
But therefore, that's why I can use the inequality star on those two guys. Does it make more sense?
Yeah. And I want to say hello to our someone in the chat. They're called Warhorse. They said it's pronounced crunchy. Welcome. So that's the proof. Like basically the proof's done. Okay. So I just want to a quick review before we move on. So for something to be Cauchy, right, we have to have like all the epsilon greater than 0. There exists a number n, big N, that is greater than 0. Let's take a look here so that you guys can follow along with me. Let's see, all p and q. Let me just get rid of that other comma there. Oops, didn't mean to get rid of both of them. There we go. So we have all p and q that is greater than n, and then p and q and n are of the natural numbers. Okay. And the distance is supposed to be less than, so this epsilon is supposed to be all the epsilon that we're referring to like in the beginning, right? All epsilon is greater than 0, right?
Yeah, so epsilon has to be thought as some kind of tolerance or
I think like for me it's like with the p and q part, I keep thinking that they're sets and they're probably like probably not sets, or are they sets?
So p and q are just natural numbers. Yeah.
Just natural numbers, right? Okay.
Yeah.
Okay, because I think it's because we started with set theory. That's why I'm like, I'm thinking that they're sets, and I'm like, no, they're probably not sets. Okay, so they're just numbers. They're just pure numbers.
And the way you want to think about them those are just indices.
Okay, so basically we're just thinking that they're p and q, which is basically just like thinking of them as just the points that we're concerned with. But there's also n, which is basically, I guess, the numbers within the ball that is the radius epsilon, right?
So the p and q and n are just indices, okay? So we have a sequence like x1, x2, and so on.
Okay.
And the p and q are just referring to the indices in our sequence.
Okay.
So the x2 is a point inside of our space, but the 2 is just, an indices.
Okay. Okay, so basically they're just different indices within.
Yeah.
Okay, within the numbers that we're working with, but it's all in the natural numbers. But P, Q, and N are basically. So I'm guessing N is supposed to be the amount, like, because since it has little n in it, the little n is sort of like kind of like, I guess like the indices that we see, but in the big N, it's basically all the n indices are in that, right?
So the big N is just a number. So basically, the way you want to think about it is that the sequence can be some very funky stuff at the beginning.
Yeah.
So maybe you can do, I don't know, you can do like very funny thing, I guess. What could be funny? I guess you can go in circle.
Yeah, because we said like all of n is greater than or less than n, right? So, like, I'm guessing you're just basically using n as sort of like I guess in your terms, a dummy variable to basically say, hey, this is the x that we're using n for. The little n is supposed to signify, hey, this x is in big N in some way, right? Or the category of those numbers, like the n numbers.
So maybe I can write, I mean, at least the picture on the left. So maybe your sequence is doing like some crazy stuff which has nothing to do with your limit point here. Maybe, I mean, maybe you can like go on circle for like a couple times.
Yeah.
And do like some fucking stuff.
But at some point, if it's convergence to x, and we have our epsilon, so we have our total elements epsilon there, then they're gonna exist some rank. Okay, so they're gonna exist some rank, which is a natural number. So this guy is just a natural number.
Okay.
Like it could be like, sometimes we can even tell what it is. Sometimes we can say it's 4.
Okay.
Such that for all points, so for all elements of our sequence where the indices is bigger than big N, we quote big N, they will be contained inside of this ball epsilon. Okay.
Yeah.
So basically, convergence of sequence don't really care about what happened at the beginning. I mean, it's kind of like elementary school student, you know. I mean, they can do like whatever they want during the recreation. And be like all sort of chaotic, but at some point they will have like to go inside and like I don't know, follow the lesson of the teachers.
Yeah, so like what I mean is that like the way I'm thinking about it, right, is like we have like, you know, x1 plus x2 right. But what I was thinking is that like when we think of like xn, right, we probably are thinking like things like you know, there's like x1, x2, and then probably like maybe down the line we think of xp, and then xq, something like that. And I'm thinking like xn is sort of like a representation of all of them, because it doesn't matter what number you pick.
Not really.
Okay.
So xn will be, I mean, usually it will, I mean, right now it's kind of, we're doing the abstract stuff, but usually it would be given by like some kind of equation like that. And okay, maybe I can give you an example of the epsilon proof. So epsilon can become some kind of tolerance. Okay. Let's say epsilon is, so we take epsilon to be equal to 1/4. And the fact that, so for example, 1/n will converge to 0, right?
Okay.
That's probably what you expect. And so in order to prove that it converged for this, I mean, so in the definition of convergence, it has to hold for every epsilon, right? Like for every epsilon, there is this property that holds, right?
Right.
So if we want to, and usually you should think of them as some kind of trial. So maybe we can like show, for example, for epsilon equal 1/4, what this trial should be and why it's true. So what we have to do is we have to find some natural number such that for all rank which are greater or equal to 0, we have that. Well, I guess in the context of rational number, we can just use the absolute value.
Okay.
We would have 1/n is less or equal to epsilon. Okay. And here, I mean, here we're kind of gonna do it like hand wavy, but just from your knowledge of numbers, you should see that if you take n to be equal to 4, this works, right?
Right.
Because so see, you take n which is equal to 4, then all the n which are greater or equal to 4 will have the property that 1 over n will be smaller or equal to epsilon, which is equal to 1/4. So I mean, here the big N has like no there's nothing special. That's just like a number, right? Just like some kind of rank where our sequence are getting small.
Okay.
I mean, does this help a little bit?
Yeah, it kind of does. Okay. Because I guess like with P and Q and like N together, like because I see from the proof that we have here, because I see why you did epsilon over 2, but I see you basically wrote that the abstract distance from xn to x, like I know you picked x as sort of like an abstract parameter to basically have P go to something.
So x here is not anything. It's the point where my sequence is converging.
Okay. So like I kind of like understand the pattern. The one thing is that I guess my question would probably be why. Why is it that you picked xn and then x? Like I feel like I kind of understand why you picked x, because you want xp to basically go to somewhere, but that's not directly towards xq because of the triangle inequality.
Yeah.
That's what I'm thinking that the pattern is. The one thing that I guess like I'm wondering is that for xn, is that to just basically define that it could be any number, such as like xp or xq, or it could even be like, you know, xn plus 1 or something like that.
Yeah. So the little n here is it's written at the top here. So the little n has just one property, is that it's bigger than big N.
Yeah.
As soon as you're able to find a little n which is bigger than big N, then this will hold.
Okay.
So for example, if you go to the concrete case I was telling you, if we take, for example, little n to be equal to, I don't know, 6,
yeah,
then 1/6 will be smaller than 1/4.
Right.
Because the little n here is bigger than our big N, right? Which is equal to 4.
Okay.
6 is. So maybe here you're a little bit overwhelmed because of the abstract distance usage.
No, because like I feel like I know we have to make it rigorous in general.
Yeah.
So I thought that like, oh, if we're given a problem to prove something that's Cauchy or something that has to do with distance, I'm thinking that, oh, xn is like, in my head I'm thinking like, oh, okay, in order to write this proof down, I have to think of like xn as sort of like, oh, we need something to basically signify both xp, xq, and xn in one, like, you know, big N. I mean xn. This fact is encapsulated with the quantifier for all n, which is bigger. Yeah, which is why we have x little n. So I'm thinking that that's supposed to be like, oh, that's representing all of the x's that we have in mind for.
Yeah.
Like
why the n? Yeah. Why the n? This is bigger or equal to big N. Yeah, exactly.
Okay. All right. So.
And here maybe I can just. So maybe this condition is a little bit weird, but at the end of the day, it's just. Here I just basically spell out the definition of what it means for xn to converge to x.
Yeah.
So this theorem wouldn't be true if the sequence was not convergent, so I have to use it at some point. So
because the distance between like xn to and x is basically x is supposed to be the point where it because we're dealing with a series, right? A convergent series.
No, a convergent sequence.
A convergent sequence. Sorry. So we're dealing with a convergent sequence. Basically, like xn could be anywhere, but it just converges to like x, because x is supposed to be where it actually gives us the where it converges at, the sequence, right?
Yeah.
Okay.
Okay. Now we're gonna prove another properties of convergence sequence and Cauchy sequence. So, so now just maybe this has to be. I mean, this is something you have to make sure it's clear in your mind. So,
okay.
Converging sequence. Converging sequence or Cauchy. Okay.
Okay.
So usually what I will do is I will prove, some of the results I will prove them for Cauchy sequence, but you have to keep in mind that convergence sequence is just a very special case of Cauchy sequence. So we're gonna have those properties hold for convergence sequence, okay?
Okay.
So at least for some statement. And the following lemma is that Cauchy sequence are bounded.
Okay.
So maybe I can explain what it means to be bounded.
Mm-hmm.
So I mean, this is a this is a lemma, but at the same time, I will give also the definition.
Okay.
And this is not all this is not only for sequence, but also it works for set inside of our metric space.
Mm-hmm.
So we said that a set S inside of M is bounded okay.
Mm-hmm.
Well, there's a few ways that we can write that, but usually we will write something like that.
Mm-hmm.
Okay, maybe what's the best way I could write it? Okay, let me think. Okay, there's a kind of two interpretation you can give. I will give you the notion. I will give the notion with the balls. Okay.
Okay.
So there exists some R.
Mm-hmm.
So it's going to be some positive number. So R here can be like rational.
Yeah.
Maybe I can put so R is rational, and such that S is contained inside of a ball. So maybe if I'm doing it in the general metric space, I will use there exists some point x0 inside of M, such that S is contained inside of a ball center at x0 R. Okay. Maybe I can spell a definition of a ball.
Is that supposed to be x0 and
yeah.
R? Okay.
Yeah. So this guy will be the set of all x inside of our space,
Mm-hmm.
such that the distance between x and x naught is strictly less than R. So this guy is a ball. So it would look something like that. So if we have our x0 here, usually we like to think about like as the inequality is strict, we like to write with the boundary with like dotted line like that.
Mm-hmm.
So this guy would be the ball of radius x0. Oh, sorry, center at x0 of radius R.
Mm-hmm.
Okay. And if I said it's bounded, it just means that you can find some kind of ball which contains the whole set.
Mm-hmm.
So the picture would be like something we have maybe a set S here, which can be a little bit complicated. I don't know, something like that. But this guy would be bounded because you're able to find some. This ball is very ugly, but you get the point.
Mm-hmm.
You're able to find some ball that contains the entire set S.
Mm.
Okay.
Mm-hmm.
For example, the natural number is not bounded because you cannot. Basically every ball is contained inside of the rational, but you can always find balls which are. You can always find points which are outside of those, outside of a ball, right?
Okay. So basically, what we have so this is the definition of what it means to be something bounded, right? So
yeah.
Basically, there exists an R, which we'll probably say is a radius greater than 0. That's also a set within the rationals. There exists x naught is an element of M, which I'm guessing is a metric space, right?
Yeah.
Okay, so S is a subset of B, which I think is the ball, right? Within X0 and R. And then that is basically, okay. I think this is really interesting. So this first ball you put, right? The one that's colored, or like, I guess sketched in, with X naught in it, right? Is that supposed to be, okay, yeah, you wrote this here. So X naught is supposed to be the small ball inside this manifold here, right? Or this space, right? That you Okay.
So there's something like that.
So, okay, so S is supposed to be contained within this radius, which is R. Okay.
Yeah. And if you're able to find such a ball, then you said that the set is bounded.
Okay, that kind of tripped me up a bit. I was like, wait a minute. So, like, I had to look back at what you defined here. So, okay, so R is supposed to be the... So radius. I'm guessing the radius, and I'm guessing this big ball that we have is supposed to be Q, right? It's supposed to be the integers, I mean the rational numbers, right?
No. So okay, maybe I can give you a very concrete example. So if we're working over the rational, let's say we take a ball center at 0, and I mean what radius we can give, let's give it 1. Then it will be the set of all rational number, such that the distance between Q and 0, so I mean in the case of the rational number, it's just the difference in absolute value, will be less than or equal to 1, right? But this guy is exactly by definition the interval -1, 1.
Okay.
The open interval.
Okay. So no, because you defined the weird shape you drew as S. So I thought that the red dash line one, that's actually the radius R, was supposed to be the rational numbers, because you said
no,
R
it's just
was
a
an
ball.
element.
Yeah.
Okay.
It's just because I think it's a little bit, I mean, at least conceptually, it's a bit easier to write it, because we call it ball. So if I write just like an open interval on the line, you will see that's not a ball.
Oh, okay.
So I was kind of giving you the sketch of what it looks for, maybe higher dimensional, or at least.
This would probably be like B, right?
Yeah, that will be some kind of ball.
Okay. All right. So what's next?
So maybe I can just do the sketch. So the balls of center at 0 of radius 1 would be just the open interval like that. Okay, and so the proposition is that Cauchy sequences are bounded. Cauchy sequences are bounded. Yes, Peter?
Okay. Oh no. So I looked at the number line you wrote. That was supposed to go with your example, the B to 0 and 1. Okay.
Yeah. So this guy would be B0, 1 in the case of the rational number. I mean, that would be basically the same thing for the real numbers.
Okay.
Okay. So how do we prove that? So you will see we're going to use the hypothesis of being Cauchy. So prove. So let epsilon. Okay, so let's epsilon. Okay, here we don't really need to. I guess here we can take epsilon to be like something very concrete. We maybe take epsilon equal 1. I mean, we don't have to be too picky about which one we choose. Okay.
Okay.
And so maybe I will call it. So xn is my Cauchy sequence. So has xn is Cauchy, then we can write what it means for being Cauchy.
Okay.
So here my choice of epsilon is equal to 1, so it means that there will exist some natural number, big N, such that for all P and Q which are of rank higher than N, equal,
Okay.
I have that the distance between xp and xq will be less or equal to our epsilon, but in our case, I choose epsilon to be 1, so it will just be there less or equal to 1. Okay?
Okay.
Is that good so far?
Okay, so basically, let's see, there exists an n that's greater than 0, and all, yeah, like we typically, and then the distance from xp and xq is less than or equal to 1, right?
Yeah. So this is a definition of Cauchy when I chose epsilon to be equal to 1.
Okay.
And I mean, you will see basically epsilon equal to 1, but I mean, we don't really care. We could have chosen your favorite number, and it will also work. I mean, your favorite number has to be a positive number and it has to be non-zero. Otherwise, this wouldn't work. But so maybe I'm restraining a little bit of your favorite number.
Okay.
Well, actually, I can show you.
I'll ask after you provided the proof.
Actually, I feel generous. What is your favorite number?
I never even thought about it, to be honest with you.
Well,
my question was going to be is like, what if epsilon is a negative number? Like, you know.
Then
like,
this doesn't work.
It doesn't work? Okay. So I thought it would be like, oh, we can't do that without, say, like, we can't do that without going into complex analysis or something like that. I don't know.
Yeah, I mean, if we put epsilon, which is equal to some negative number, the condition here will be very weird because it will say that xp minus xq has to be, for example, less or equal to -1, but that's impossible because the distance is always a positive quantity.
Okay.
So this is, so even if the sequence would be constant, this would still not work.
So literally with negative numbers, we break it. That's basically what happens. Oh, okay. Never mind.
Yeah, so that's why we have to.
I thought it would go into another branch of math that is like much higher than that. That's why I asked.
No, I mean usually you want distance to be a positive unless you're doing.
Okay, gotcha. Okay.
Okay. But well, if you don't have positive, then it's not really a metric space, and you don't really get the sum properties. So it's
right. Yeah.
Okay. So we'll take epsilon equal to 1 because I guess you don't have a favorite number, but okay, we're gonna assume it's 1 your favorite number because you're the number 1 Twitch math streamer. Right?
No. There are many others that can take that title. I don't think I'm one of them.
So this guy is a natural number. Okay.
Okay.
So basically, what's gonna happen is that they're gonna so basically they're gonna have finitely many terms which are less or equal to which are indices less than n. So we're gonna have x minus 1. So those guys are finite, right? There's exactly n minus 1 term, n minus 1 element of our sequence which our indices is less than n, right? So what we're gonna do is we're gonna put some quantity. We're gonna call it m.
Okay.
And m is gonna be the maximum between the distance between xi. Well, maybe I can write it as the way I put stuff. So x1, xn.
So is it xi and xn?
So I will just put x1 and I will do it like the way I just
x1. Okay.
wrote. Yeah. dx2, xn, and so on. Okay.
Okay.
And the point is that as I have as I only finite indices while the indices is less than n, then this guy is a finite set, right? So I basically just have a set with distance, with n minus 1 distance, and as it's a finite set, I can just take the maximum of them.
Okay.
Okay, so I'm gonna call the maximum m. And okay, maybe I should haven't called it m. Okay, maybe I would add a little something in my set. Okay, I would add a little 1 at the end. Okay.
Okay.
And so why I did that is that now m has to be less or equal. It has to be bigger or equal to 1. because 1 is inside of this set, so the maximum has to be bigger or equal to 1.
Okay.
And now I will show that. Not what I will show. I will show that all xn are inside of the ball centered at the xn of radius m.
Okay.
So maybe I should not call this guy m. Maybe I will call it r because maybe a little bit more intuitive with the proof. Okay, that's my claim.
So the ball is like xn and m, right?
Yeah.
Or x. Oh wait, hold on. So wait, it's xn and r.
Yeah.
Okay.
So maybe I can show you a little picture of what is going on. So what's gonna happen is that so for every p and q which are bigger or equal to n, I have this bound, right?
Mm-hmm.
Maybe I will put a little star below it. So maybe I will have xn, and then here I have the balls of okay, I have a ball like that, of radius 1. And I have like all the higher terms, xp and xq are inside of those, right? Inside of this bound. Okay. So those guys are kind of well behaved because they're like kind of stuck inside of this ball of radius 1.
Right.
Those who are not well behaved are those that come before, because those I cannot control them.
Okay.
So x1 can be like somewhere like that, x2 can be somewhere like that, and x3 can be something like that. You know, they can be very far apart from xn, right?
Okay, so why are they not well behaved in this case?
Because I mean, the convergence of a sequence just look at higher term. I just look at higher indices, right?
Oh, so wait. So is it like you're like thinking about the sequence as if like because you have to go at like I guess like quote unquote an infinite amount of times, the radius is basically just like too expanded if you just started out like with say x1 and x2 and x3, but then when you get to much higher values, it basically shrinks the radius. Is that what you're
Yeah. They get stuck inside of my ball.
Yeah.
That sounds very weird to say that, but
you said it, not me.
Okay, maybe here I will I kind of underestimate the space it's gonna take.
Yep.
And basically what I did with my maximum set that I put there is that I look at distance. So the thing is those points which are before the xn.
Yeah.
So those whose rank is less than n, there's only finite many of them.
Okay.
So those guys are trouble, but there are only finite many of them, so I can take care of them separately. And what I did is I said, okay, let's look at distance between those troublemaker and the xn. Okay, that would be some kind of thing like that, right? Wait, I have to be a little bit careful. I think I will be fine. Okay.
So it's x1 to xn, right?
Yeah. So I look at the distance between those guys, and so this guy will be x and minus 1. I mean, you get the point. I just look at the distance between all those troublemaker, and I say, okay, who is the worst among you? Maybe there will be x1. I mean, at least in my drawing, it looks like it's x1, right?
Yeah, it looks like it because it's the longest.
So what I will do. So this guy will be my r. This will be my maximum.
Okay.
And what I will do is I will look at the balls centered xn of this radius.
Okay.
So it would look something like that. Okay.
Okay.
And as I chose like the worst case possible, the one which is the furthest away from xn, that all the other guys should be like well behaved and they should be inside of the ball like that I just draw.
Okay.
Okay, so this is like the if you want the picture of the proof that we're doing right now.
Okay. Yeah. So basically, what you're doing is that no matter the distance, whether it be x1 or x2 or x3, you're basically taking the maximum of the radius is actually the maximum distance between those, because since they're so spread out, you're basically what you're trying to do is that no matter how close you get, like it's basically like the radius is always going to be there. It's going to be any distance, even though the ball is shrinking, the closer you get to the parameter you want, such as epsilon is equal to 1.
Yeah. Okay, here I did a small mistake though.
Well, what's up?
Here I'm not supposed to take R, I'm supposed to take 2R. That's just like, that's just because the fact that that the balls does not include the boundary, right? So if I chose R, so if I chose my radius to be exactly R, then this guy wouldn't be inside of the ball because it has exactly a distance.
It's at the edge,
Yeah. So I have to make it a little bit bigger, so I can take 2R, but I could have chosen a 5R and just make it marginally a little bit bigger. Then you'll be happy.
Okay.
Okay. So this is the pictorial picture. Now let's prove it.
Okay.
Formally. So I mean, here you kind of see there's like kind of two cases, right?
Yeah.
There's those troublemaker which come before the big N, and there are those which are after, which are very well behaved.
Yeah.
So let's do the proof. So show that for all N, x of N is inside of the ball x on 2R. Okay. So so we're gonna have two cases. So if N is strictly less than big N, okay. Then so this guy will be among so those guys will be among the finite xn will be among the little troublemaker, right? But we know that R is given by the maximum between x1 xn, and as n is smaller than n, what's gonna happen is that this guy will be in the list, right? So this guy is inside of the list. So what it means that that the distance between xn and x with a big N like that will be smaller or equal to R. Okay. Because this guy is inside of the list I just wrote.
Yeah.
But as R is not 0, then we know that 2R has to be strictly bigger. Therefore, dxn is smaller or equal to 2R, which is equivalent to the fact that x is inside of the ball center at xn of radius 2R. Okay.
Okay, so where did XR come from?
xn.
Oh, that's xn?
Yeah, sorry.
Okay.
So where does it come from? It comes from my bad handwriting.
Oh, okay. So it's x big N, and then is that supposed so the xn is an element of b xn. What is after xn?
2R.
Oh, 2r. Okay, okay. I was like, why is there
2 times
Z?
the radius.
Why is there a Z there? So, you wrote 2r because basically you want to include the edge, right?
Yeah. So
Okay.
the 2 is just. I mean, I could have chosen something else. I could have choose like 5/4 times r. That would have been something fine. But,
so it had to be bigger than just r itself, right?
Yeah. Just marginally a bit better.
Oh, okay.
So I choose 2r, but I mean, as I said, you could have chosen 6. It wouldn't have done much of a difference.
Mm-hmm.
Okay. So this showed the case when n is strictly smaller than big N.
Okay.
So now we have to do the other case, which is when little n is bigger or equal to big N, right?
Mm-hmm.
So here we can use our bound star, which tell you that if n is bigger than n, then the distance between xn will be less or equal to the distance of xn. I mean, this distance will be less than 1.
Okay.
Okay, so in the condition of being Cauchy, I have P and Q.
Mm-hmm.
Usually I have like P and Q which are bigger than n. Here I took P to be equal to n, and Q I took to be equal to big N.
Okay.
So that's why I get this bound. Is that clear to you?
Let me see. Here. So you're just replacing. So you're basically saying you replace P with N and Q with big N, right?
Yeah.
Because it's in the maximum. I mean, in the radius, which is the maximum of the distances that are within that.
Well, that's not the reason. The reason is because of the little star bound that I have above, like at the beginning of the proof. Yeah, maybe it's been a while since we.
Okay, so all n is greater than n, and then this is it. Right. Okay.
So I can choose P to be equal to n because n is bigger or equal to big N, and I can of course take Q to be equal to big N itself because
they're bigger.
N is equal to itself.
yeah, it's bigger than or equal to n. So basically, it doesn't matter if you basically just pick P or for little n or Q to big N. It just makes the point of the proof here.
Yeah.
Okay.
So I have this guy, and now we can use the fact that you said that 1 is among the maximum.
Yeah.
So does R, which is the maximum, is bigger or equal to 1?
Okay.
Okay, maybe I should have written the other way around. So 1 is less than R, or equal to R. But if we want strict inequality, we can just multiply it by 2 and then we get the same thing.
Mm-hmm.
Therefore, excess inside of the ball of radius center at xn of radius 2r. And now we're done. So, I mean, I kind of like this proof. So, basically, higher indices are well behaved, and the troublemaker are those finite.
Yeah, it's actually you can visually see it. Yeah, you can visually see it, which makes it a little bit easier. Let's see. All of P and Q are greater than n, right? The distance between is. Okay, so basically we just established that that's like less than or equal to 1. I'm just basically running it through, so I basically see it. Because I also written all this stuff down, so I'll just like look it over on the screen on my tablet here. So R is less than or is greater than or equal to 1. We will show that side the ball. Show that all of n is an element of the natural numbers. Xn is an element of n. So okay. If n is less than n, then we know that. Okay. Therefore, distance here. Okay, if n is greater than or equal to n, So I think what I want to ask is that when you show that n is little n is less than big N, right?
Yeah.
I know you're basically showing like a scenario when that does happen, but I'm guessing that's why you put the 2R there, because you just want to show that there is an R, but it's going to be less than, it's going to be less than, I guess, a bigger parameter that we're going to be talking about, right?
Yeah.
Because since n is less than, little n is less than big N, it's going to be a much wider radius, right?
Yeah.
So then you basically are saying that there is going to be a bigger radius, but the radius, the distance within xn, x little n to x big N, is that it's still less than or equal to the radius that we have in question, but it's just going to be, but you're still comparing that radius to a bigger radius, which it could be because the numbers, or at least the subscripts, are less than what we got in the smaller circle, right?
Yeah.
So you're just showing that, right? That's basically what, because like, it could be that n is less than, little n is less than big N.
Yeah, but I already did this case.
Yeah. So, but you're just basically presenting that case because you have to, because it's like.
Yeah.
Okay.
Yeah. So as I said, in this proof, they were a troublemaker and they had to tackle them.
Yeah, you have to basically show that there are those that basically make the series the sequence kind of like go out, like not really be convergent, because there's just single numbers.
Yeah.
Let's see. I think that's okay. So, and thus so the case where little n is greater than or equal to n, then basically it would be less than 1. Thus, 1 is less than or equal to r, and so one epsilon is also equal to 1, right?
Yeah.
So is this one here supposed to be the epsilon that we just...
Yeah, exactly. Yeah. That's the epsilon that we showed at the very beginning.
Okay. So basically, in this type of proof, epsilon has to be like less than the radius that we have in question.
Well, we could have chosen something different. For example, maybe I can do a little bit of a change to the proof. So let's say you took epsilon to be equal to 6.
Yeah.
I mean, he doesn't really care. It just has to be something positive. Then the proof would look something like that. So this guy will have now the bound 6, and this guy will have the bound 6.
Mm-hmm.
And in my set where I will have the maximum, at the end I had a 1, right?
Uh-huh.
Now I would just replace the 1 by 6. And
let's see, proposition, the Cauchy sequence is bounded. Okay, so our condition was that it's bounded, right?
Yeah.
That's basically what we were trying to prove here, right?
Yeah, we're trying to prove it's bounded. Yeah.
Okay.
So yeah, I mean, you could have chosen epsilon to be anything, so I chose 1. But
the structure is usually like
it's exactly the same, yeah.
To be bounded, it's like this, right? Or like we'll just put.
It's contained inside of a big ball. Yeah.
It's like this type of structure, right? Where it's like epsilon has to be the smallest.
I mean, here I don't really rely on epsilon, right? I mean, I just use a specific epsilon at the start just to get some bound, but after that I didn't really care about that.
Oh, okay. Okay.
And even the epsilon I chose doesn't really matter, so I chose 1 because I was like, well, let's make it simple.
Oh, okay, yeah.
Okay, now we get to the core. So we've shown that Cauchy sequence are. We showed that convergence sequence are Cauchy, and it's quite natural to ask if the opposite is true, because the fact that the sequence are bounded is kind of saying that the sequence is somewhat nice, right?
Mm-hmm.
And so here I have a definition, and as it's a definition, you will probably guess that this will usually fail. A metric space MD is called complete if all Cauchy sequence are converging. Okay.
Okay.
So you mentioned a few times in some stream a while ago that you mentioned that R has the property of completeness. This is exactly what it means.
Metric space.
It means that all Cauchy sequences are also converging sequence.
Okay.
So for a complete metric space, the two notions are the same. And here's is kind of the trouble. I mean, here we're gonna have. This is the question is gonna be of interest for us now. Is Q a complete metric space? And the answer to that will be no.
Okay.
And that will be the reason why we need to define the real numbers. So for example, if we don't have Cauchy sequence and converge, the series is completely hopeless, and we cannot get like very nice. I mean, for example, sequence that are like bounded and increasing should be converging. Well, if this metric space is not complete, then this is not necessarily the case. So analysis doesn't really work if you're not working over a complete metric space.
Okay.
And maybe on a higher note, to give you a kind of a landscape view of what is analysis in general. So at some point, people will care about space of function, and the reason why, I mean, if you're like a physicist or the guy in the 19th centuries or before, is because you want to solve PDEs. Okay.
We got someone in the chat. Hey, non-dairy neutrino. I forget, does the completeness require the Cauchy to converge to an element in the space, or just converge at all?
So it would mean it converges inside of the space M.
So it has to converge to the metric space.
Yeah, inside of our metric space, yeah. I mean, right now it's kind of weird to think about it because we only have the rational number. But once we get the real number, we're going to see that basically the rational number were missing points.
Yeah.
And now when we're going to look at the sequence of rational number that are Cauchy, they will be convergent, but they will not necessarily converge to a rational number. They will converge maybe to an irrational number.
Yeah, something that's not part of it. Yeah.
Yeah, that's why probably his remark come from.
Okay.
And the completeness property is which is very important for doing analysis. For example, the whole theory of Hilbert space and Banach space require us to have complete metric space in order to do that. They're not exactly. I mean, there are a special case of metric space when they're given by norms or scalar product.
Yeah.
In the case of Banach and Hilbert space, but yeah. So usually it's really hard to do analysis when you don't have completeness. Like many theorems that you will see. I will do like one concrete example of. I will prove like I will build a sequence that converts to square root of 2, and basically I will show like exactness of some algorithm that can do that. And you will see I will kind of struggle because I don't have my usual tool from real analysis because the rational I'm lacking like a lot of tool in my toolbox.
Okay.
So we'll see. So the end question is no, but this kind is not very convincing. I just basically write in a angry fashion. I just wrote the word no. So we would like to have an example to that. But before that, I don't want to go straight up to an example because if we go right now, it's going to be complicated because we don't have we don't have tools in our toolbox.
Okay.
Like right now, like now in our toolbox for showing that the sequence is convergent, we have like basically a rusted screwdrivers.
Yeah.
So maybe we want like some nails and other stuff to help us.
Non-dairy neutrino typed in, if the space is compact, then you'd get all the Cauchy sequences converging to an element in the space. It's quite a while since I've done my real analysis.
Yeah. Okay. So in the sheet I gave you for this weekend.
Yeah.
For the I guess the weekend that just passed.
Yeah.
I gave you some exercises which are similar, and basically there's like two kind of proof that we have to do twice. Yeah. And basically I leave you like the other half to you to do it.
Okay.
But I will show you. Okay.
Okay.
So before we were kind of doing stuff on general metric space, but now we're gonna specialize the case of rational number because we have a little bit more structure that we want to use. So here's a proposition. I might just prove the first two because they're the most important, and the other I might leave as an exercise. But I might help for the division case because it's kind of hard. So let xn converge to 0, xn yn converge to y, be converging sequence of rational number.
Okay.
So as I said, now I'm quitting the metric space journal's perspective, and I'm going to the rational number. Sequence of rational numbers. Oh, where I live right now, there's like thunder.
Oh, okay.
I heard like a big boom outside.
Oh, I didn't hear it.
Yeah. I think the weather is quite nice today. I think it's like 25. Degrees Celsius.
Yeah.
You might say, "Oh God, that's cold."
No. I know what you mean. I know Canada uses Celsius.
Yeah. And okay, so what is the proposition? So it's the thing that you use to basically. So if there, I said converging. Okay, I will change a little bit my. Well, I could show the converging part. I don't know. So basically, what I will show is I will show that sum of convergent sequence is converging. But I also need to prove that the sum of a Cauchy sequence is a Cauchy sequence. So I think I will do the Cauchy part, and as an exercise in the sheet, I leave you the converging one here. So let's xn be. Maybe I will just rewrote everything because it's getting confusing. Let xn and bi be a Cauchy sequence. Inside of Q. Okay. And so the point is that over Q we have a little bit more structure than a usual metric space because we have also the structure of a field, so we have addition. And what I will show is that the sum of two Cauchy sequences is again Cauchy. So maybe I should write stuff like that instead. Writing. So is again Cauchy. Be the product of two Cauchy sequences again a Cauchy sequence.
Okay.
What's the one that I'm missing? Oh, I need the division. So, okay, here we have to do some hypothesis. So, if yn is never equal to 0 for all n, then xn over yn is Cauchy. Well, I actually don't really need C though, so I will just prove A and B. C is more useful when it's about
Is B supposed to say like xn times yn
yeah.
is again Cauchy? Is that what you?
Yeah.
Okay.
And basically you will have the same statement. So maybe I can. So those are the exercise for this week. A prime P B prime. So if you replace the word Cauchy by convergent, you will have that the sequence f of x plus y of n converge to x plus y, while x of n converge to x and y of n converge to y. Okay, and you have and for the product you get the same thing. It converges to the product of the limits. Okay. So those are probably like, I mean, the last two is probably things that you already used in the calculus class a few times. Sum of limit and product of limit. But basically, I will prove the case for Cauchy, and the convergent case I leave as an exercise. But if you take if you look carefully at what I'm doing right now, those two guys should be quite easy to do.
Okay.
Okay. Okay. So let's prove A. So so my goal is to show that xn plus yn is Cauchy. So let's epsilon be a positive number. So okay, maybe I will not write that. Okay. So let epsilon be a positive number. Now I want to show that xn plus yn is Cauchy, which is equivalent to say also goal. We want to find a big N bigger or equal to 0, such that for all P and Q, which are bigger or equal to N, we have that XP plus YP minus X. So here I will put I go to parentheses here. Oops. This is supposed to be a Q, I'm sorry. There you go. Is less or equal to epsilon. Okay. So now I don't have the distance anymore because I'm working over the rational, so the distance is just given by the absolute value. Like that. So I get that. That's my goal.
Okay.
Okay. Okay. How do we show that? So we're gonna play with the triangle inequality.
Okay.
The usual stuff. So so first of all, let's use the fact that x1 and xp and yp are both Cauchy sequence.
Okay.
So has xn and y and are Cauchy. So they're gonna exist some natural number. So as I'm doing for both, I will have two natural numbers. Okay. And then I will get a similar bound to the one I have here. So I will have for whole n which are bigger or equal to an x. I have that. Oops, sorry, not this. I'm supposed to write P and Q. I'm sorry. I have xp minus xq, which is less or equal to. And again, I will do the same trick as I did before. I will choose epsilon over 2.
Okay.
So this is one of my bound that I will use. And now I will do exactly the same thing for the y. Yp minus yq is less or equal to epsilon over 2. And maybe we can call this bound double star. Okay?
Okay.
So we basically just enumerate the Cauchy condition. And now, so we want to find a big N, right? That's the thing we want to show. That's in our proof, right? In our goal, at least.
Yeah.
And here I kind of have two things that I can choose, right?
Yeah.
But I want to choose my N such that those conditions with all those that I can use star and double star. So what I will do is I will choose N to be the maximum between those two. Okay. Therefore, if I chose P and Q which are bigger or equal to N, I will be able to use the star and double star inequality because P and Q will be bigger than NX or N and Y. Do you still follow?
Yeah, you're basically just you're basically like, I guess, not limiting, but you're kind of like solidifying the fact that XP or like basically P and Q like are basically the distances that we need in order to get to epsilon.
Yeah. And I will play with the triangle inequality.
Yeah, that's what the reason why you had it at epsilon divided by 2.
Yeah. So what I will do is I will play with. So let's see. I will use the triangle inequality on. So I will write as the following. I will write xp minus xq plus.
Is it like YP? Like YP?
Yeah. YQ. And I mean, if we write, what is it? I mean, what if I write what is this quantity? Just the quantity I can write.
Yeah.
XP plus YP minus XQ plus YQ. Okay. But now here I have a sum, so I can use the triangle inequality on those two sums. So the triangle inequality will give me this the following: XQ plus YP minus YQ. Okay.
Okay.
And now I can use, so as I said, P and Q are bigger than NX and NY, right? So I can apply star and double star to get the bound I want. So if I apply star, and here I apply double star, I will have the bound epsilon over 2 plus epsilon over 2, which is epsilon. Does XP plus YP minus XQ plus YQ is less than or equal to epsilon. Therefore, Xn plus Yn is Cauchy. Oh my god, there's like a lot of rain outside. It almost feels like when you have like summer, like very intense weather, like when it's very it's really hot outside, you get like a storm like that in the afternoon. Hold up. Okay, I'm back. Okay, so this showed that the sum of Cauchy is Cauchy. And now we are, okay, this one I don't remember by heart, so I will try to guess, and maybe you will have a better idea how we usually structure those proofs when we don't know in advance the bound. So let's show B. So I want to show.
And this is to show that xn times yn is Cauchy, right?
Yeah. Okay. So, okay, here I will do a sketch of the proof because I don't remember the proof by heart, so I will play with inequality, and once I'm done with the experiment part, I will jump to write the formal argument here. So it will give you a better idea how it's done under the hood.
Okay.
So the thing I care is okay. So here it will not be a formal argument at first. So I will just write stuff and just think while writing stuff, and when I'm done, I will write the formal thing. So I want to control this guy. That's the thing I care, is to be able to control this quantity.
Yeah.
Okay. And the things which are given to me is that. Oh yeah, okay. I remember about the trick for doing that. Okay. So this is a very famous trick.
Okay.
What we're gonna do is we're gonna add some quantity and remove it at the same time.
Okay.
So we're gonna do something like xp yp. Maybe I should use another color to say what I had, what I remove. So we're gonna add. Let's see. Well, I guess I can do it like that. Yeah, something like that. You will have to play a little bit. Okay, do you see what I did? I just add, so in green I just add the quantity and I immediately remove it.
Okay.
I still get the quality because I just hadn't removed the thing that I had at the same time. So the thing on green is just a funky way of writing 0, but I'm gonna use this. And probably what I want to do is start to factoring some stuff. So maybe I can have something like, so if I factor xp, I will have xp times
be like yp plus yq.
Yeah, actually, I will just switch them around. I will want those guys instead. Yeah, the thunder is pretty. I kind of like the thunder. Hopefully the electricity don't go down. But
hopefully.
Other than that is.
It's kind of funny because I think like theoretical physicists, when they were trying to, I think they were trying to figure out how to get like quantum gravity out of like the equations they got. It was like thundering lightning, and then thus string theory was born at that point. So maybe we're on a verge of discovery here.
Maybe we are. All right.
And then factor out yq, right?
Exactly. So I will put it at the front. So I'm gonna have xp minus xq. Okay. Now I can probably assume that I use the fact that yp and xp verify Cauchy, so they will probably have like the absolute value of yp minus yq is less or equal to epsilon, and I will do the same for this guy. I mean, as I said, it's a sketch of a proof, so right now I don't worry too much about the detail. Okay. So I mean, once I've done that, I have got two sums. So the obvious thing to do is use the triangle inequality, right?
Right.
And factor out the xp. So I will get something like that: yp minus yq plus yq xp minus xq. Okay. So now I will be. So what I will have if I use the bound I have on those guys, I will get xp times epsilon, and here I will have yq times epsilon, right? And what I will be live with is that I will have xp plus yq times epsilon, right? And I'm almost done, right? The only thing that bothers me is that I have xp and yq, right?
Yeah.
But I will use one of the facts that we proved today. We proved that Cauchy sequences are bounded. So as Cauchy sequence are bounded, I can find an M which is strictly positive, such that for all n, in n I have the absolute value of xn is bigger or equal to m, and I can do the same thing for yn. Okay. I mean, what we showed today is that we can do it for one sequence, right? But if I wanted to for two sequences, what I do is I apply the result for each sequence, and then I take the maximum of the two. That's how you get. That's how you find those constants.
Okay, so this last part, right? You basically said you're going to keep them bounded.
Yeah, because I know that Cauchy sequences are bounded, so I can do the thing I wrote at the bottom.
You can find an m that is greater than 0, such that all of n in n is less than m. So I think this part I'm like, does this actually make this go away? Like basically, this part?
So what's gonna yeah, so basically if I take from this part, now what I have is that so I can remove the xp and the x cube by m plus m, right? Times epsilon. And now I'm done with 2m's times epsilon. Okay.
Okay.
And okay, so now you see we don't have epsilon, right? At the end we get like epsilon with some other stuff, right?
Right.
And this will motivate us. So one way to fix that is so at the beginning we have that xp minus yq was less or equal to epsilon, right? So what I will do, I will change the epsilon for something else. When I will write the proof, instead I will ask that xp minus yq is less or equal to epsilon over 2m.
Okay.
And when I will do the algebra like I just did before, I will now end up with an epsilon instead of a 2m epsilon.
Oh, okay. So
that's how that you saw that like in other proof I have something like 2 epsilon over 2, right? I chose. It's because I did like a sketch of proof like that before, and then I realized that at the end I will get 2 epsilon if I don't divide by 2 at the beginning. So
so when you say it's bounded, it's basically like saying like, oh, it equates, or it's either equivalent or less than the metric space that it's on, and thus
so m is just a number.
Oh, it's
so
a
maybe
number.
I should use the word should use r. Sorry. Times r times epsilon, and here we'll have 2r. Okay. Okay. So this was the sketch of the proof. Now we'll actually write the proof. So formally, so it's kind of funny, this proof, because you saw like what is going on under the stage, and now you will see the final product if you want. So let epsilon be a positive number. So our goal is to find an n bigger or equal to 0, such that for all p and q's that are bigger or equal to n, we have that xp yp minus xp guy's supposed to be P. This guy's supposed to be Q. Is less or equal to epsilon. Okay, that's our goal. And so what we're gonna do is we're gonna basically use the sketch of the proof that we used before.
Yeah.
So we're gonna restate the argument. So has xn and yn are Cauchy, then by one of the previous position, we know they are.
What's supposed to be? Let's see. Has xn and yn Cauchy, then by one. What's after the one and I'm guessing this is proposition.
Yeah. Oh gosh. I guess that. Wait. I don't see the.
Yeah.
Okay. I see. Okay. It's right. Wait. Hold up. My. My escalator is doing some funky stuff.
Okay, yeah, because it cut off when it's like one and then some stuff, and then I think it was you were trying to write proposition, and then
yeah,
no, yeah, it kind of cut off there.
Okay, maybe I will do like the thing I did last time. So can I find you on the? Okay, so what? Okay, here for me right now, you have like a blank space. So what is written right now in front of your cursor?
I still have everything you wrote. It's just that one part is like cut off, such as
okay. So what?
Like the one, and then I just wrote proposition here because I think you wrote proposition here.
Okay. Maybe I will just rewrite the sentence below because I don't really see what I have. So
yeah.
Yeah. Skedra is not happy right now. Okay. Has xn and yn are Cauchy sequence, then they are bounded okay. Am I like writing on stuff, or am I like
No, I see it.
Okay. Are bounded, so this is by a previous position, the one where we had troublemaker. Therefore, there exists some R, which is strictly positive, such that for all natural number, we have that xn is less or equal to R and yn is less or equal to R. Okay?
Okay.
Basically the thing we discussed before.
Mm-hmm.
And now we're going to use the fact that so as xn and yn are in Cauchy, we again use this fact.
Mm-hmm.
Then there exists again rank nx and ny, which are positive numbers, such that for all p and you kind of see the trick last time when I had like two sequences. I have nx and I have ny, right?
Yeah.
And I took the max, right?
Uh-huh.
So basically I will no longer do that because you kind of see the trick that I can just take the maximum and everything works fine. So from now on I will just take n and I will just assume that it works for both sequences.
Okay.
See? Because otherwise if I have an nx and an ny separately, I can just take the maximum and begin.
Okay.
So now we'll just write this. Such that xp minus xq is less, and now we're gonna use the trickery that we saw in the sketch proof. We're gonna hash it to be epsilon over 2r, and the same go for yp minus yq. We're gonna hash it to be epsilon over 2r as well.
Okay.
And now we're just basically gonna do the algebra we did last time. So we had xp yp minus xq yq. Yeah. Here I should probably let LP and Q be bigger or equal to N. We have this quantity, and we want to show it's less or equal to epsilon now.
Mm-hmm.
And now we do exactly the same thing we discussed in the sketch. So we're gonna introduce the new quantity, and we're gonna remove immediately. So what was it? It was
I think it was
XP
plus.
I think it was something like that. Alright. And now we can factor out the XP, the first term. YP, YQ. And the other guy we can factor as a YQ. And now we're going to use the triangle inequality and the fact that when you have a product inside of absolute value, you can just take out the product. So we have XP, YP, YQ plus YQ, XP minus XQ. All right?
Mm-hmm.
And now maybe I will just color code the bound I have. So those bound I will call them star. This guy will call it double star, and this guy will call it triple star. And now if I use all of those, I will get that XP is bounded by R, so we just have R. So the YP, YQ, this guy is bounded by epsilon over 2R. And the other guy is bounded by, so YQ is bounded by R as well, and the other guy, XP minus XQ, is bounded by epsilon over 2R.
Okay.
And now if I simplify the algebra, so the RC cancel out, so I'm left with epsilon over 2 plus epsilon over 2, which is equal to epsilon. And then we're done. So maybe we can just write does XP YP minus XQ YQ is less or equal to epsilon. Therefore, it's Cauchy. All right. So you saw, so this, I think this one was very good because we had like a few ideas that we had to take in.
Mm-hmm.
I mean, first of all, you saw like a sketch of the proof, so it kind of you kind of saw how it's usually done in practice.
Yeah.
And you also saw how I was able to. So, I mean, I cannot see the sketch of the proof that I wrote, but you saw like I was trying to play with inequality.
Yeah.
And then I was like, oh, okay, I have this term which is a bit annoying. Can I do something about it?
Mm-hmm.
And I asked those XP and YQ, which were a bit annoying, but then I used the fact that my sequence is bounded to basically get rid of them.
Yeah.
And at the end of the day, I chose. You saw why I chose the bound double star, the bound triple star, right?
Yeah.
Yeah. So I think it was quite valuable because I mean sometimes in textbook they just show you like the finished product,
mm-hmm.
and then you look at the proof and you see, well, we're gonna use the little bound epsilon over 2R.
Uh-huh.
And then you're like, where does that thing come from? And like when you simplify all the algebra at the end, you get the epsilon you wanted, so you're happy.
Mm-hmm. Okay. Yeah, I'm like looking over, so like XP and YQ, like the factors that we had in the second step,
yeah.
These two, right?
Yeah.
So so they're bounded, right? They're supposed to be bounded, Cauchy sequence, right? So when you say they're bounded, right, you basically say they just like go towards a number. Is that basically why the R appears
Yeah, so the R is a bound for them. So, I mean, maybe I can draw a little picture at the bottom. So you have your Cauchy sequence will look something like that.
Yeah.
Anyway, something like that, x1, x2, x1. But we show that Cauchy sequences are bounded.
Yeah.
So what it means, I mean, okay, it was not exactly the way I wrote it before in the general case of metric space, but when you have an origin like that, like 0, so the fact that it's bounded just means that we're able to find a sphere that will, not a sphere, but a ball that will encapsulate our
radius,
sequence, right?
Yeah, a radius of something, right?
Yeah. A radius maybe R.
Yeah.
And if you want to, if you want to work with inequality, what it would mean that the absolute value of our xn is less or equal to this radius.
Okay.
So that's basically the idea of what it means to be bounded.
Oh, okay. So basically, like it's like either less than or equal to. So the thing of it is that I know that there's such thing as bounded above and bounded below, as well as just plain bounded.
Yeah.
So I'm guessing because it's the absolute value, basically it'll just go to like R, right? So that's why you have the absolute value symbols in there.
Yeah. Yeah.
Okay.
So those guys are really bounded. They're like from both sides they're bounded.
Oh, okay. Let's see. So you don't have to clarify that in the proof, right? Because I just noticed that when you're writing the proof formally, you basically just automatically say XP and YQ are automatically R regardless. Like you didn't have to write like basically because XP and YQ.
Yeah,
you didn't really have to clarify that, right?
Yeah, I could have written it, but right now I had like 4 inequalities, so I kind of just.
Is that the point where like a math professor would be like, if you wrote this, like this part, it would be like they would write like obviously.
I mean, not. I mean, if I want to be a little bit more politely correct, what I should have written is that this bound followed by. Okay, now it's gonna be a nightmare by little star. 1 double star, triple star.
Oh, okay.
And then I will be fine.
Oh. Okay.
And maybe for going for this line to this line, I mean, if we're like beginner, I should probably write something like by triangle inequality.
Oh, okay.
But it's a good habit when you start to write them, so you can see all the things that you use.
Right. Yeah.
While doing that. But over time, you get lazy and you don't even mention that you use the triangle inequality because it's like, oh yeah, it's basically like any other Saturday, you know.
Oh, okay. I see. Oh well, this was a very informative lesson. We learned more about the Cauchy sequence since we were talking about it like a lot last week. But yeah, I'm.
Maybe I can just give a corollary in 4 minutes.
What?
I can just give a corollary of that, so a consequence of that.
Okay.
So maybe we can write Cauchy Q as the set of Cauchy sequence.
As the set of a Cauchy sequence?
No, of Cauchy sequences. So an element of this set will just be a Cauchy sequence.
So what I see on my screen is basically Cauchy Q as the I don't know what this part is.
It's set.
Oh, it's a set. Okay. As the set of Cauchy sequences, right?
Yeah. And what we've shown is that element of that will be like sequence. So an element of that will be a Cauchy sequence. And what we've just shown in the last in the last proof is that we just shown that actually Cauchy sequences are closed under addition and multiplication.
Okay.
And so if we write Cauchy sequence as this has a ring structure.
Okay.
This is a ring. I mean, basically, okay, for showing it's a ring, I have to show other properties, but I mean, the other properties are kind of like very easy to check.
Yeah.
For example, the multiplicative identity will just be the sequence xn, which is always equal to 1, and so maybe this would be the 1 sequence, I guess. And the natural element for addition will be the sequence which is always equal to 0.
Okay.
And you can check, in fact, that addition and multiplication are associative, and all the distributive lines, all the stuff you're supposed to write to check. But I mean, those are very easy because you already know they hold inside of the rational. So they basically just say, well, it's all for every term, so it has to hold for the whole thing. And so the hard part was to show that when you take a sum of two Cauchy sequences and a product of two Cauchy sequences, you still get something which is Cauchy. And this gives us the ring structure.
Yeah.
And basically, next time it's going to probably be very weird for a course in analysis to do that. But next time we're going to do ring theory.
Ring theory? Okay, so that's the next part, right? That's tomorrow, right?
Yeah. And the reason why is because essentially the Cauchy sequence. So a cool thing with Cauchy sequence. Okay, on Wednesday we're going to see a cool activity where we're gonna learn a little bit more intuition about them, but Cauchy sequence basically, so the fact that they do not converge sometimes because like the domain might missing points, tell us that Cauchy sequences are able to see those missing points.
Okay.
So Cauchy sequences are not very far from being the real numbers in this sense. Yeah. But there's kind of an issue with them is that, for example, as Cauchy sequence, the sequence xn, which is equal to 0 for n is equal to 0 and 1 otherwise. Okay. As a sequence, xn and the sequence which is always equal to 1 are not the same. Because at the 0 indices, they differ, right? So if we took the Cauchy sequence as the definition for the real number, we would get a lot of duplicates. Okay. Because I mean, if you think of like Cauchy sequence as real number as like the real number they represent is like their limits in some sense. Yeah. You would expect that xn and the sequence which is constantly equal to 1, those two guys should be equal, right? Because the two are converging to 1, but as Cauchy sequence, that's not the case. So we would have to mod out, but we would have to have some equivalence relation to make those things now equal in the quotient. Okay. And basically, this will be the definition of the real number. So we're gonna have the real number is equal to Cauchy over Q over some stuff. Oh, okay. And the stuff that I'm gonna present next time, so this construction is something that you do a lot of time in ring theory. Is called the quotient ring. Oh, okay. And one advantage of that of using ring theory is that if I have a ring and I quotient it by something that I will explain next time, the object that you get at the end will automatically be a ring. And if the thing by which I quotient have some special property that I will mention next time, you will automatically get a field. Okay. So basically, the reason why I want to do ring theory next time is because I could just completely ignore the ring theory part and just do the quotient without caring about the addition structure and multiplication. Yeah. But now I will have to do the real number by scratch because now I will not have addition and multiplication for the real numbers anymore. I will have to define them. But if I do it as a ring quotient, now it comes for free. Okay. That's why I want to do it ring theory next time, so we can
That sounds very interesting. Yeah, because like.
Yeah. And also, I mean, again, next time I'm gonna give you example because ring theory is kind of abstract, so I'm gonna give you some example, and you're gonna see like a lot of familiar construction can be made up from this. So with the construction we'll describe next time, we will be able to construct the modular numbers.
Yeah.
Like z mod n and stuff like that. And also, I mean, I guess we were sort of cheating, but I mean, once we build the real number, it will not longer be cheating. But we'll also see how the complex number are made of this construction.
Okay.
And I think it's going to be interesting. And probably one of the example I will give you, the very two concrete example I will give you is the Z mod 2 example and the example of construction of the complex number with the quotient.
Okay.
Because the real number is somewhat a bit more complicated than those two, but if you understand the easier case, then it will give you insight about the a little bit more complicated case here. But yeah.
Okay, and the way you're going the order, because like I think it's pretty good because it's not like a conventional real analysis course where they just basically don't introduce rings at all. They just basically just go into go into the deep abstraction and just build it from scratch, which is probably like a little bit cumbersome. Yeah. Basically, it's because I don't want to spend too much time. I mean, one of the things you want to know with the real numbers is it has to be a field, and I don't want to spend like another lecture and checking that. No. I appreciate that actually because it feels different because like with like a class it feels terse, so it feels as if like, oh man, like when are we gonna get into the more interesting stuff within math, like rings and like different types of abstractions that I think most mathematicians talk about, but most undergrads don't get exposed to because like they feel like, oh, real analysis, I have to know this to get to because it's a prerequisite to the next courses.
Yeah.
So it doesn't feel like it's actually like, it feels like we're learning the advanced math a little bit through real analysis, which I think is really, really a good change of pace, I think.
Yeah.
So Sascha, do you have anything to say to our global audience before we end today's stream?
So I have to remember all the things. So leave a like, subscribe, drop a follow on Twitch, drop the bell.
And join the Discord server.
Oh yeah, okay. I was missing one.
yeah, that's fine. It's fine. So like for all those on Twitch, I will basically post a Discord server in there, and also I will put my YouTube channel in there. And if you're watching this on YouTube, all the links will be in the description down below, including my Twitch channel and my Discord server, as well as my game channel. If you just want to pop in and basically say hello. My Twitch video game channel, if you want to pop in and just say hello. But yeah, once again, Sascha, thank you for the awesome lesson today. I tried to follow as much as I can, and also like whenever I don't reply back, sometimes it's because I'm just writing in my notebook. But I also record these lectures so that just in case if the stream breaks too many times, I can just upload the videos there. But luckily we only lost connection I think once, but
oh, okay.
Yeah, we only lost once, so it was okay.
Yeah, I think it's getting a bit better compared to like 2 weeks ago.
Yeah, I think it's because the seasons were changing. That's the reason why it would break so much. But yeah, like don't worry guys, like if it breaks too many times, I'm literally recording each lecture because it's for my own notes, but also for your guys' benefit. So if it breaks too many times, I will upload my version of the stream. The reason why I don't is because because my internet is not that great, so the upload speed would be very, very slow, and you guys probably won't get the lecture until like probably the next day. so that's just a forewarning. But yeah, once again, Sascha, I will catch you tomorrow for tomorrow's lecture, and once again, thanks for the awesome lecture. But I think the last thing I'm going to ask you before I get off of Discord is, do you want to actually give the title for what I put in the thumbnail for this lecture? Because I think.
Well, it depends. Do you want a lot of views or no views?
No, because I think what we did with each, because I would make the thumbnail and I would put like I think what you introduced for each lesson on it, but it's something that's like not, because it's not like part of the original title. So let me look at my thumbnails here, because like the last I think the last lecture you did, I called, like I put in the thumbnail sequences in metric spaces. So because like I think when we were talking about the negative numbers, I put in the thumbnail rings to rational numbers. So is there a particular I guess catchphrase that you would like me to put in the thumbnail, since you were the one to give the lecture?
Well, I guess today's lecture was more about Cauchy sequence, so it can be Cauchy sequence something.
Yeah, so Cauchy sequence.
I guess we can go for the meme and say, is it a Cauchy sequence or a Cauchy sequence? Or... I don't know.
that could be it, or maybe like I'll try to think of something, but it'll have. But you want something involved with Cauchy sequence, right?
Well, I mean, yeah, that's kind of a descriptive name, so.
Yeah. I'll figure something out.
Yeah, I mean, you're the mastermind behind the titled name and titled thumbnail.
No, it's like I look at the overall thing that we do, and then I'm like, what is the most interesting thing that Sascha said throughout the whole lecture? And then like I'm surprised that with the negative numbers one, like I basically thought of rings to rational numbers, because like and like, you know, sequences to in metric spaces. I was like, oh, that sounds really mysterious but cool. I think for the one with negative numbers, I basically put like, you know, bracket, you know, the pair of C and 0, and then equivalent to like C to 0 and C. So, you know, like I left it a little wide open there.
Actually, I'm quite I'm quite curious. Which point right now, I mean, among all the things we did before since the start of those lectures, which part you found, which lecture you found the easiest, and which one like you found the harder / interesting?
Well, I'm not gonna say they're easy. For me, it's like you explain it pretty well to me, so I kind of like understand what you're explaining. But when it comes to actually applying what you explained to me, that is a much harder task.
Yeah. This required a lot of.
So for me, I think the most interesting, like I can't answer the easy question, but I would have to say the one that I found the most interesting was when you were saying we have to introduce rings to explain the rational numbers. I thought that was interesting, including like equivalence relations with negative numbers, like using equivalence relations with negative numbers. And I was like, oh, okay, so relations do play a part in it. And I thought that was pretty interesting because it actually explains why math, or at least numbers, have this, you know, like what is addition, what is subtraction, what is multiplication, and all that stuff. And it all involves like relations in some way. If I'm saying that right. Yeah. So I thought those, I think like you always give me like a little tidbit to basically make it feel like, oh, there's this little fact you don't know about the math rules you know, and I'm like, oh, okay, and that's why I find it very interesting. So I think every lecture is interesting because there's some little thing that I did not know and I just learned. So, you know, that's why it's called Math Spellbook, guys. You see the magic unfold. Sascha is just basically the wizard to let us know about that, because he has the experience. And, you know, like if you want to learn from him, as well as I do, you can pop into our Discord server, and sometimes like he happens to be in the voice chat. But you know, that's basically how it goes. So Sascha, thank you again, and I will see you tomorrow.
Nice. Yeah. Take care.
All right. Take care. All right, guys. That will do it for today's stream. Let me see. I want to see if we can rate any of my fellow math streamers. Let's see if they're, because I felt like we haven't done a raid in so long. So, oh, Fizzbuzz is streaming. We'll probably give them a visit. So thank you guys for dropping in today. Like I said, all the links are in the chat if you're in Twitch, lurking. And also, if you're watching this on YouTube, all the links will be in the description down below. So I'll put in the raid command right here, and then do the raid command here for FizzBuzz, and we'll set that up. Okay, cool. Oh, and thank you for joining me today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys on FizzBuzz's channel. So take care, guys. Bye-bye.